Welcome back, guys, to our second round of a flipped classroom. The last time when we did our video, we were learning about sampling methods and possible biases associated with those sampling methods. Tonight, we're going to be looking at experiments and observational studies. So we're shifting our gears a little bit in terms of the type of data that we're gathering and also how we're gathering the data based on the questions that we're asking. So for example, if we were sitting in class right now, I would probably say to you or ask you, what aspects make the following description an experiment? Now you guys have been and sat through multiple science courses. So what makes this an experiment, right? And when you're looking here, it says, do plants grow better in a different light? To answer this question, I will use 5 small pots of the same size. I will make sure they have drainage holes at the bottom. I will fill each pot with soil and will moisten the soil and let the excess water drain. I will then sprinkle 8 to 10 ordinary radish seeds on the soil, followed by about 1/4 inch of soil over the seeds, and then I will water it again. I will water very lightly every day. The day the radish seeds sprout, I will place one pot in a different location. For example, the kitchen window that has some sun, outdoors in the shade, outdoors in the sun, in a well-lighted room but with no sun, and in a room that is not well-lighted at all. Once a week, I will measure and write down sizes in different pot locations. When you're taking a look here, okay, when we're saying to ourselves, what makes this an experiment? Some of you might say, well, it's a control group. Or you might say, well, we're taking a look and we're putting them in different locations. And it's all of these pieces together. However, the biggest thing that makes this an experiment is that there is something that is being imposed onto, in this case, the experimental units, which are the plants. Experiments are when we impose a treatment onto our subjects, right? And in fact, it's usually when we want to figure out if there is some sort of cause and effect between an experimental unit or between those and then the treatment that we're trying to impose. So when you're saying about what makes this an experiment, though, while all these things are really important, there's a lot more to describing an experiment. There's lots of different types of experiments that we can produce. And there's lots of different ways to gather that information. So therefore, what we're going to be looking at first is talking about that experiments versus those observational studies. So you're seeing here, again, from that following thing, our goal is what are we looking at, what are experiments and observational studies for today. So we're actually going to start in the land of what is the difference between an observation and an experiment? Because we do make observations in an experiment, but an observation is not an experiment. And when I say that we make observations an experiment, that's kind of like our loose colloquial kind of like wording, right? But when we look at an observational study is actually when we observe outcomes without imposing any treatments. There's no assignment of a treatment to a certain group. This is not an experiment. In order to be an experiment, you must be imposing a treatment. If you're not imposing a treatment, it now becomes an observational study. So for example, observational studies can show correlations. They can show that one thing is leading to the other, or there's a connection between the two, but there is no causation. So for example, music education and grades. You might have heard through multiple backgrounds that an increase in a music education leads to an increase in grades. It's not that one is causing the other, but there may be a correlation between having music education and having higher grades. Experiments, on the other hand, have to actively impose or assign some sort of a treatment in order to observe what we call the response, right? The response is usually what we're measuring at the end. Again, experiments are the only thing that shows causation. That is a very popular AP question where they say which of the following can show that one causes the other, and you are literally just looking through the choices, looking for that experiment. So, when you're taking a look here, are the following a study or an experiment? You can read through these three choices, these three questions, and you are going to decide, was this a study or was this an experiment? At the beginning of class, we will check our answers to these three questions. So let's talk a little bit more about studies, or specifically observational studies. There are two different types of observational studies. There's a retrospective study, and there's what we call a prospective study. A retrospective study first identifies your subjects who perhaps studied music, and then collects data on their past grades. Think about retro, from the past, something in history, okay? So we identify subjects, and then we collect information about them based on things that happened in the past. A prospective study is very different. That's when I would identify my subjects now, identify them in advance, and then I would collect the data as the events unfolded. So perhaps you want to follow a freshman class. I would identify the freshman class this year, and then maybe I would watch them as data unfolds over the next 4 years. But again, I would not be imposing a treatment. I would just be collecting data that already pre-exists without imposing some sort of treatment to that particular group. So while that's all fun, and observational studies are definitely handy when necessary, I think the one type of study that comes in the most often is definitely experiments. So let's talk about this one for a second, right? Here's my example how we talk about experiments here. So let's say I have a rabbit, okay, and I've developed a new rabbit food. It's called Hippity Hop, okay? So really fun rabbit food. And I'm going to make the following claims. I'm going to say, hey, it makes the fur soft and shiny on my rabbit. It increases the energy of your rabbit, so more hopping around. And 100% of the daily vitamins and essential oils needed for my bunny rabbit to grow and to become even bigger and hear better and all of the above. So the question is, am I allowed to just make these claims about my food for the bunnies? Can I just say, hey, it's going to make the fur soft and shiny? The answer to that is absolutely no, right? If you go to the market or if you go online and you look at these products for all different things, so many companies make claims, but we have to ask ourselves, did they test these claims? Are they true? So no, you can't just make these claims. You actually have to test them, right? But what do I have to do in order to make these claims viable? How do I know that they're the truth? Well, you'd have to perform an experiment, right? Now the question becomes, who or what should I test this on, right? So if I'm testing rabbit food, I should test this on, well, rabbits. That makes sense, right? And what am I testing, right? Or what do I test? Well, I'm testing the type of food. I want to see if the food works, right? What we're looking at here, okay, what we're talking about in these questions are experimental vocabulary that we need to know. So for example, when I say to you, who or what am I testing on? This is what I call an experimental unit. This is the person that I'm testing. What am I testing, or what do I test? The type of food in this case. Okay, that is our explanatory variable, right? That is our factor, or that is our explanatory variable. And then we also have different levels for each of those variables. So when we're taking notes here, okay, experiments study the relationship between two variables, right? Experimental unit is the single individual, person, plant, etc., to which the different treatments are assigned. Note, people can be called subjects if you're using subjects in an experiment. We also have what we call a factor. The factor is the explanatory variable. This is what you're testing. In the case of the Hippity Hop food, the food itself was the factor. We were testing to see if the food was a factor. In terms of the level would be a specific value for the factor. So perhaps in your experiment, there might be a group who didn't get the food. There might have been a group who got half of the hippity hop food dosage, or there might have been a group that got a full dosage. So the level is the quantity of the factor or specific value for the factor that you are providing. In addition to these vocabulary words, we also want to make ourselves familiar with the vocabulary of a response variable. A response variable is what you're measuring. So for example, we're trying the hippy hop food. I want to see, does it make their fur shinier? Does it make them stronger, right? I want all the claims that I made in the slide from before. Does it increase their energy? These are the things that I'm looking for in terms of the response variable. The treatment itself is an specific experimental condition applied to the units. So it is the combination of the factor and the level, and that is specifically what is being applied to the experimental units. So coming back to this idea of hippity hop food, right? I want to test my food. I want to test my new rabbit food. What are my experimental units? That's the rabbits. What is my factor? That's the type of food. And the response variable is how well they grow or how shiny their fur is, depending on what we're looking at, right? So then I might say, all right, well, I'm going to test this food out on a bunny. And I'm going to say, all right, well, here's the hippity hop food, right? And I'm just going to use my pet rabbit, Lucky. Since Lucky's coat is shinier and he has more energy, then hippity hop has to be the better rabbit food. So taking the food, giving it to my one rabbit, and then I ask myself, well, if that's the case, is this a good experimental design? Hopefully your answer along with mine is no. Because I've only tested this on one rabbit. I would need some form of a control group, a group that is used to compare the factor against. It can be a placebo or it can be the old or current item. Okay, but there has to be something to compare it to. I can't just give the food to my one bunny rabbit and say, hey, because it made this bunny's fur shinier, that's going to make all the bunnies' fur shinier. Also, we don't know if it's just a change in seasons. Maybe their fur is just changing because it gets getting colder or warmer, but we want to take this all into consideration. When you're talking about a placebo in terms of your control group, a placebo is some form of a dummy treatment that would have no physical effect on the outcome. So for example, a lot of times if they're testing medications, you might get a sugar pill or you might get a pill that is made up of something that would not impact whatever they're measuring. Okay, so let's take a look at my new experimental design. So now let's say I have my hippity hop food, okay, and I also have the old food. And you can see here, I clearly have two different rabbits, right? I have my rabbit Lucky again, but now I'm going to also use my friend's rabbit Flash. Okay, so Lucky gets hippity hop food and Flash gets the old rabbit food. Wow, Lucky is bigger and shinier, so hippity hop is still the better food. So my question to you is this a good experimental design? I clearly now have a control group. I have a second rabbit to test it on. One gets hippity hop, one gets the old food. Is this a good design? Hopefully we're taking a look here and saying, well, no, this doesn't work because I have two types of food and two types of rabbits. I'm not giving both types of food to both rabbits. Lots of things going on here that's not working for us, right? Also, one is a big rabbit, one is a small rabbit. So the idea here is that we need to be able to replicate, right? We need to be able to replicate this experiment, just like we had to be able to get a sample size that was large enough. So now let's say I've had now multiple bunnies, right? So I'm looking at the big bunnies and the small bunnies. I have hippity hop food and I have the old food. and I am going to catch the first 5 rabbits, right, that I can get to. And then the first 5 rabbits I catch are going to get the hippity hop food, and the remaining 5 will get an old food, right? And then perhaps we'll see the hippity hop rabbits have scored higher, so it has to be the better food, right? This has to be what's going on. So my question to you is this a good design? If I just catch the first 5 rabbits that I can get to. And hopefully the answer here we're all getting to is, well, no. Again, Mrs. Rodriguez, no. Because think about the rabbits that you're able to catch and think about the rabbits that you're not able to catch. If you're talking about the first 5 rabbits that you can catch, that you just get to in a room, these are probably maybe the bigger bunny rabbits. They might be slower. They might be more prone to human interactions. If these are the rabbits that you're able to get to physically, right? And then we're assigning them to the hippy hop food, we might just be getting these results because those bunnies had something in common. So the same way that we've been circling back to this idea of randomization and probability, it is not sufficient for me to just catch the first 5 rabbits that I can catch because that is convenient. But that has no form of randomization that's going to help me produce a valid experiment. So instead, let's number the rabbits 1 to 10, okay? We are then going to place the numbers in a hat, okay? The first 5 numbers pulled from the hat will be the rabbits that get hippity hop food. So I'm going to put rabbit number 9 in hippity hop, 7, 5, 8, and 3. The remaining rabbits get the old food, right? And then once I randomly assign them, then I'm able to evaluate the rabbits and found that the rabbits eating the hippity hop food are better than that of the old food. What we've actually just done here is we've changed this experiment so that we hit all the principles of the experimental design. Here are the 3 components that are necessary for a good experimental design. 1, we need to have some form of a control. So notice we went from only having hippity hop to comparing hippity hop to the old food. We have a control of effects by extraneous variables on the response by comparing treatment groups to a control group or a placebo or some sort of old product. In addition to having a control group or something to control the extraneous effects of outside variables, we also want to use randomization, okay? Randomization in experiments comes in when you're assigning your subjects to your treatments, okay? It's not about randomization of the treatment to the person, but the subject to the treatment itself. In addition, we cannot have one person in each treatment, but rather we have to be able to replicate the experiment on many subjects to quantify the natural variation in the experiment. These are very important. So there are different types of experiments. What we just looked at before, when we take all of our subjects and we just randomly assign them to each treatment, we call that a completely randomized design, right? So just number your experimental units and randomly assign them to each treatment. That's a completely randomized design. However, there's also a design that is also helpful to us called a block or a block experiment, okay? When we're talking about this is when we group similar individuals together and then randomize within each of these blocks that we can remove much of the variability due to the difference among the blocks. Blocking is an important compromise between randomization and control, but unlike the first 3 principles, it is not required in an experimental design, but can be very useful to us depending on what we're testing. Okay? So now, let's say I want to take my hippity hop food, okay, and I make all these claims, and I want to say that it makes the fur soft and shiny and increases energy for all types of rabbits, right? Can I make this claim? Can I say that based on my experiment that it works for all rabbits? As long as you follow that experimental design, or all the experimental design principles, we can extend our claim from not just our study to the entire population. The only way for us to show cause and effect, okay, is with a well-designed and well-controlled experiment. Okay. In addition to the 3 questions of study versus observation, observation versus experiment, you are going to complete examples 1, 2, and 3 about the vocabulary here about factors, levels, response variables, and how many treatments. I'm going to skip through some of these slides. You can probably even check your answers here, but we'll talk about them tomorrow in class. And now I want to go back to the OptiGrow, because now when we're coming back to the OptiGrow, we want to talk not just about experiments in general and what makes a good experiment, but now I also want to talk about what are the different types of experiments, right? How can I design experiments differently to answer different questions? Well, let's take a look at the example that we'll be focusing on when we talk about the types of experiments. We're going to talk about an ad from OptiGrow Plant Fertilizer claims that this product you will grow juicier, tastier tomatoes. You'd like to test this claim and you'd wonder whether you can get by with half of the specified dose. How can you set up an experiment to check out the claim? So our question is, what are the different types of experiments and how can we design these experiments to test different claims that we want? When you're dealing with an experimental design, like mentioned before, the completely randomized design, all experimental units are allocated at random among the treatments. Notice here there's an explanatory variable. Okay, in this case, it might just be your experimental units. Notice here, I've just added in that there would be these arrows indicating that I would be randomly assigning my experimental units to each of the treatment groups. This one happened to have 3 treatment groups. There could be more or less. And notice at the end, after I assign them to the treatment groups and I gather the information, we are gathering and analyzing a response variable at the end, right? So let's take a look at something like this. Let's say I had 4 different treatments, okay? And let's say we wanted to look at a completely randomized design, okay? For a completely randomized design, I'm just going to randomly assign experimental units to treatments. So I might number them, randomly generate numbers, ignoring repeats, but essentially I'm just randomly allocating all of my experimental units to each of the 4 treatments. Okay, so you would generate numbers depending on how that would work or how many units you have in order to go from there. Okay? That would be a completely randomized design. The diagram for OptiGrow, see if you can fill in for the plants and the experimental units what this would look like in terms of making your diagram for the experiment for the experiment of testing, whether the OptiGrow fertilizer makes your plants juicier and tastier for your tomatoes. On the first line to the left side, you would want to put your explanatory variable. So that could just be, your tomato plants, right? And then you would randomly assign your tomato plants. So in the first little arrow on the left, we would put random assignment and we would be randomly assigning them to maybe tomatoes that get 0 dosage of the fertilizer, tomatoes that get half a dosage of the fertilizer, or tomatoes that get a full dosage of the fertilizer. And then at the end, we would test their taste test and their juiciness. However, if you wanted to add more factors into that design, it could look something like this. Let's say we get 12 tomato plants from a garden store. Let's say not only do I want to test the fertilizer, but I also want to test the quantity of water, that they're receiving as well. So notice here, I now have not just 3 treatment groups, but perhaps I would now have 6. So I would take my 12 tomato plants, I would randomly assign them into 6 groups of 2. There would be a control fertilizer dose with no water, half a dose of fertilizer with no water, a full dose of fertilizer with no water, a control group with water, half a dose with water, full dose with water, and then again at the end I'm going to compare the juiciness and tastiness. All of this, while it's written here as a diagram, could also be written in paragraph form. So you could also say I'm going to take 12 tomato plants from my garden and randomly assign them to the 6 different treatments, and then describe the 6 treatments, and then provide that with, at the end, the comparison of the juiciness and tastiness. Notice here, okay, the added factor or the added thing that I'd be testing would be whether or not there was water provided to the groups. So what if our units had a distinguishing characteristic, though, that needed to be taken into consideration for the experiment? Think about like if you had a survey, right, and there was a pre-existing condition that would need to be taken into consideration that I should have separated them into. So very similarly to what we call the stratified random sample for surveys, we have in experiments what we call a randomized block design. Units are blocked into groups. They should be homogeneous, just like strata. But remember, this is an experiment, so we don't call it strata. And then we're randomly assigning them to the treatments. By doing this, what it does is it reduces the variability from group to group, because I'm controlling these differences that I know will have an impact on my response variable. So for something like this, okay, I could take my experimental units, I would split them first into homogeneous groups called blocks, and then I would assign them to the treatments. Do recall, however, that the important thing here is that the random assignment does not occur when I'm breaking it down to the blocks, but rather when I'm assigning them to the treatments. Okay, that's the big takeaway here. And then at the end, I'm still comparing my response variable. Again, units should be blocked on a variable that affects the response. If the variable is not going to affect a response or affect the outcome, then it's not something that we need to block on, unless we need to see if it has an impact. We can also do that too. So let's take a look here. Let's say now I only have treatment A and treatment B. Okay, and you take a look at my experimental units, and there's clearly blue smileys and pink smileys, right? So one thing that could impact my study could be the color of the smiley face. So I might first want to put the smileys into homogeneous groups. So notice I separate the blue from the pink. It's doing its magic. Magic, magic. Okay, and then now I'm going to randomly assign them to the treatment. Sorry that popped up behind it. But notice I'm randomly assigning the blue to treatment A and to treatment B. And then I randomly assign the pink to treatment A and to treatment B also. This is a randomized block design. So when we're looking at the OptiGrow plants, let's say we bought tomato plants from 2 different stores. So let's say one came from store A and one came from store B. What we could do is first block them into where they came from, randomly assign them to the 3 different fertilizer levels, and then at the end we would compare the juiciness and the tastiness. Notice here the blocking is done based on the store from which they were purchased. Okay, there's one other type of experiment that you guys have seen quite a bit, but it makes sense to talk about it in a little bit of a different way because it's not as traditional. Matched pairs, okay, is a special type of design, but it's a special type of block design. Matched pairs typically happens when we match up our experimental units according to a similar characteristic and then randomly assign the treatment to we're assigning it to the experimental units, and then the second experimental unit in the pair will get the treatment. You have each unit do both treatments in a random order, and the assignment of the treatment is dependent, right? Because it depends on who got the other one first. Examples of this would be taste testing, match pairs. If my taste buds were testing something before and after, if we paired people up based on their level of activity and then saw how long a new pair of shoes lasted or something like that, that would be an example for a match pairs design. So let's take a look here, back to our smiley faces. How is this going to become a match pairs design? Well, if you notice here, the smiley faces are a little bit different because now they're not all smileys. Some of them are sad, some of them are neutral, and some of them are happy. So what we're going to first do is we're going to pair the experimental units according to specific characteristics. So notice here, I have blue smileys, blue sads, right? Everything is paired so the smiles are, so that the faces are the same. Next, I'm going to randomly assign one unit from a pair to treatment A, and by default, the second unit is going to get treatment B. So if you notice, every time I split up a pair, one goes to treatment A first, and the second one goes to treatment B automatically. But notice they had something in common. So now when I look at the faces in treatment A, they're going to match perfectly with the faces in treatment B. This is one way to do a match pairs design. Another way is to have the same individual unit do both treatments, such as in a taste test or before and after. Okay, but that's another idea for a block design. So other things that we can do to make our experimental designs even better, right? Think about what do you think would happen what do you think if your results would be affected if the subjects were aware of the treatment that they were receiving? When we are trying to make it so that the subjects are unaware, we call this blinding. Okay, in order to avoid the bias that might result from knowing what treatment was assigned, we use blinding. Okay, there are actually two main classes of individual that can affect the outcome of an experiment. So, for example, those who could influence the results, that means the subject, the treatment administrators, or the technicians. Okay, but there's also those who evaluate the results. So like the judges, the treating physicians, etc. When every individual in either one of these classes is blinded, an experiment is said to be double blind. Okay, when every individual in either one of these classes is blinded, it's single blind. When both classes are blinded, then the experiment is called a double blind experiment. It's very important to differentiate between single blind and double blind. We hear this a lot, especially when you hear like medication commercials and things like that. They talk about this double blind studies. Listen to those medication commercials, and you'll hear that a lot. But blinding is used a lot so that when we are looking at our results are not biased, because neither the person receiving the treatment, the person giving the treatment, or even the person evaluating the treatments have their biased inputs on the results. Okay? It's important to remember that when dealing with controlled treatments, we used previously the word control to limit the extraneous sources of variation by keeping them constant. But often we really want to compare a situation involving a specific treatment to the status quo. So remember, control treatments are really important because it provides us with a baseline measurement or controlled treatment, and the experimental units to whom it is applied is our control group. We do use often in these scenarios placebos. Okay, often simply applying any treatment can induce an improvement. So for example, like a mother's kiss to a child's knee when they're hurt, right? I know so many times with my son, I ask him, do you want mommy to kiss it to make it feel better? And in his mind, that just makes the pain go away. even though that's not really technically doing anything. Also, to separate out the effects of the treatment of interest, we can use a control treatment that mimics the treatment itself. We can use a fake treatment that looks just like the treatment being tested, and that's called a placebo. Placebos are the best way to blind subjects for knowing whether they are receiving the treatment or not. In addition, don't forget about experiments and samples. Okay, these are actually two different things, but they do have some stuff in common. So experiments and sample surveys use randomization to get unbiased data, right? So whether it's assignment in the experiments or selection in samples, there is some aspect of randomization for us to be able to use those different types of probabilities. In addition, they do differ in different ways for different purposes. Surveys are to estimate population parameters, so the sample needs to be as representative of the population as possible. However, experiments try to assess the effects of treatments, and experimental units are not always drawn randomly from a population. Sometimes we are specifically choosing a certain set of people to see how those treatments affect a particular group. So, experiments and samples, similarities and differences, focusing on this slide. But best thing for us to come back to, overarching, because it does come up in a lot of multiple choice questions, is really asking, what are the best types of experiments? What are important for experiments to be the best? Well, there has to be some form of randomization or random assignment. It has to be comparative, usually to some sort of control group. The best ones are double-blinded so that there's no bias in the evaluation or the receiving of the treatment. And also there should be some sort of control group or some sort of placebo in the cases that are necessary for us to be able to compare results so that the experimental units are not having an impact on the results themselves or on the response variables. All right, so I know this was a lot of data, vocabulary even in terms of experiments. Tomorrow I'm going to start by going over the questions I asked you to complete through the slides. If you have any questions, please bring them to class also. We will be starting the class off with those concepts, and then we will be delving into more AP practice centered around experimental design. So this could be what makes a good experiment design, what the different types of experimental designs, the different parts of experimental designs. We're going to see this all through multiple choice questions and free response questions. But hopefully this is helpful, and we'll get into practice when I see you guys next.